I'm guessing a little bit here that you're working on the extra credit. I think that's where.
Okay, well, let me just tell you kind of my perspective on it. I don't think okay, I'm taking 4 classes right now.
Wow, 4 math classes.
Yeah, 4 math classes.
Wow.
But I'm still trying to make it so that I'm not having to work over like 40 hours a week on school.
Yeah.
So this last week, I worked like 55 hours on schoolwork, and I had to say, you know what, that's it. No, I'm working too much. This is too much. So I just said, I'm just going to take whatever grade we get on Monday. But if I can just get some more time on this test, then I can.
Oh no, I wasn't. No, we got till what, Thursday.
Yeah, no, I really appreciate it.
That's not the problem. It's the problem is on my end. I made some error because the extra credit problem involves the geometric distribution. Okay. And I really want to give that to you, so you can, if you decide to go for that, you can do. That's the last step.
Yeah, I appreciate it.
The Last Temptation. What was that book? The Last Temptation of Konstantinopoulos. How do you pronounce this? Konstantinopoulos, whatever. Anyhow, so my goal is to try to get to that geometric distribution, but I have to wrap up what we were doing on Thursday. So,
sure.
So yeah, but you definitely you're missing a tool to finish off the extra credit. Absolutely, it's not hard, but I can't. I gotta do it in context. So let's see if we can finish off quickly that binomial distribution problem. How did that go? Do you guys remember the components? What was that problem? I hate to use notes, but I have to make my old brain move fast here to get to the test. So this was example 6F, right?
Right.
And the question was, you had 2 machines, and they would function incorporate if greater than half of the components, so those dots in there are functioning, and these are all independent, right? So all you had to do to solve the problem, it asks, okay, exactly how it says, for what values of P is a 5-component system more reliable? So this guy working here, the probability of it working, it'll work with 2 good or 3 good. So those 2 cases, the probability of operation, the probability of operating, if it's going to work and incorporate is, if 2 of them are good, so we have to do 2 cases on the binomial. Okay. Now, why is this the case? Well, the 2 good ones could be these 2, or these 2. So there's 3 different cases, and that's the way that is. Now, the 5-component system will work if you have 3, 4, or 5. So there's 3 cases where the whole thing will work because you have more than half of those cases. So this is 5, choose 3. This is a case of only 3 of them working. This is the probability that you get exactly 3. And remember, it was greater than or equal to 3, so you could also do 5, choose 4. And P to the 4, 1 minus P, plus 5, choose 5, P to the 5th. Okay, so we wanted to know when this was more likely, this probability is higher than this probability. This is the probability of this one working, this is the probability of this one working. So what we needed to do was put the symbol greater than here between this and this. Okay, let me check the chat. Chat looks cool at the moment, but we have low attendance. I suspect that's due to the test. Okay, so how far do we get with this? So again,
that's where we were at. We didn't solve it yet, but we got to the realization that, oh well, this is just an equation with 1 variable, and it's a polynomial. It can be solved.
However, if it's a 5th degree polynomial, we could be in
it could be nasty, but it can be solved.
It can be solved. How can we? Yeah, I don't know how to do this quickly. It's so you want, these are the 2 things. So unfortunately, I have to rewrite here, because this is, I don't think this way on two different lines, so I'm doing algebra. So we want to know when the 5 component one's better, so we really want to know this. And this is not going, this is, I can tell that this is not a good, this is going to be a problem. I'd like to be able to do this, but I feel compelled to do something different. Okay, maybe with your help, we can do the algebra here super fast. Okay, so this is what I want. I just rewrote this. Hopefully I rewrote it correctly. So we could lower the degree of the polynomial here, right? By doing what?
Dividing everything by, let's see here, p squared. I think everything has a p squared.
Yeah, so and this is 3. Let's divide by p squared, and let's try to just not do everything at once, but watch me that I don't do something stupid here. And why can I divide by p squared? Well, I'm not interested in the case of p equals 0. Okay, so, right, so we can sort of assume that's not the case. So what does 5 choose 3 anyhow? Is that 10?
Yeah.
This is put on your super duper algebra mind right now. So that's 5 times p squared times 1 minus p plus, what's this, p to the 5th. Okay, don't trust me to not make a mistake.
I'm doing it on my own paper too. Although at the end you shouldn't have p to the 5th. It should be p.
Thank you. P cubed, right? We're divided by p squared. Good. Okay, so what do I do next? Tell me what. Let's collect.
I checked my own work because I think I might have made a mistake somewhere. You have 10p times 1 minus p. Where'd that come from? Oh, there it is. That's yeah.
Well, let's try to do it. Let's try to do it this way. Let's go 0. Let's try to do it in place. So let's look at all the. So what's the highest exponent of p? Let's put that in. That would be what? P cubed, right?
Mm-hmm.
So that takes out that. Now let's look at how many p. What do I have in terms of p squared?
So you want to multiply out the 10 times that to get p cubed.
Oh.
10 times p times 1 minus p squared.
Okay, you know what?
Do we want to just?
I'm not doing this very well. So how many p cubes do I have? I get 10 p cubed for this, right? And then I have minus 5 p cubed. What is it? That's 5 p cubed, right?
Yeah, minus
so
5.
6. It looks like 6 p cubed. This is a nightmare for me. This is not my strong suit doing algebra. It doesn't even look like a cube. Every evil is about me right now. Okay, so are we good with that? Because look, you've got, hopefully, we still have a low depressed attendance. I believe it's got to be the test. Okay, so was this correct? Minus 10 p cubed. Huh? No, plus
Yeah.
10 p cubed minus 5 p cubed. That's 5 p cubed. So 6. I think this is correct. What about p squared? So what do we have in terms of p squared? So you have minus 2. Minus 2. If you get a minus 2p here, that's not minus 20p squared. That would be minus 20p squared, and then you have a 5p squared. Isn't that minus 15p squared? Is it? So
I'm working on it. I'm not as you're still going faster than I can go.
I don't see how that's possible. But yeah, I can see the 5p squared, but I'm looking at the minus 20p squared here. So it seems to me it's minus 15p squared.
Okay. So I see negative 20p squared plus. Okay, so yeah, so I have negative 15p squared.
Thank God for that. And then what about how many p's do we have? This could be the killer. So you have minus 3p plus p, which is minus, that would be a 2p if you bring it over here. So you have a 2p, but there's a 10p part of this. So isn't that 12p?
Yeah, I got 12p.
And are there any constants involved here?
Yes.
-3 or something?
Mm-hmm.
There's no sense in my looking at my page here because it's just okay. So what do we? Assuming that's correct, what would we do next?
Next, we take that and we put it into a calculator.
Oh, I was gonna just divide out.
We can divide by 3, yeah.
Yeah, so 2p cubed minus 5p squared plus we divide by 3, so that should be 4p minus 1. Okay, now this is old school here. Assuming this is right, doesn't look right. I mean, maybe it is, but assuming this is right, we don't look for a root, right, to bring this down to a
If
quadratic.
we want to look for a rational root, it would have to be it would be the factors of the left number and the right number.
What if we put a 1 in? I mean, just right, using that.
Just test it.
Yeah, because it's quick for us to do it. If we put in a 1, that might be the quickest way to do this because you would end up with a 2 minus 5 plus 4 minus 1. So it looks to me like 1 is a root.
Yay. Then we've done it.
We're not totally done, but we're very close to being done because I need to use what? I need to divide out by that root. So let's see if I have space.
Yeah.
So 1. And what are the? So we have 2 minus 5 minus 5. I'm using synthetic division. 4 and minus 1. And what do I need to do? So you bring down the 2. And you put a 2 here. It's a minus 3. 1 times minus 3 is minus 3. That's a 1. It's a 1 with 0. So it looks like this guy here is what? P, 1 minus p, right? 1 is the root times what? 2p squared minus 5p plus 4. No. Hold on a second. Do it again. No, it's down here. So times p squared minus 3p plus 1. And how to, there should be a 2 here. There's a 2 here. This is the only time I've had to use synthetic division since I was in,
I don't even bother because there's just so many things to keep track of. So I just use long division each time.
But anyway, we can factor this. 2p minus 1 times p minus 1. So you have minus 3. That's it. Okay, so we actually have the answer now because the only way this is going to be negative, not positive, is if 2p minus 1 is less than 0 because you have 1 minus p squared. Or, well, you don't really have. Well, there's a minus. Oh, okay. This is. Hold on. It's supposed to be p minus 1 squared. I don't know why. Why did I do this? This thing was p minus 1. So
yeah, p minus 1.
This is not a great day for me. This is p minus 1, and so this was the. I don't know why I did that. So anyhow, it's p minus 1 squared. So the only way you can get this negative, in fact, it's going to be positive if 2p minus 1 is greater than 0. When is that true? If p is greater than.
Excuse me, yeah, greater than 1/2.
Yeah. So it turns out this is an interesting solution to this. If p is bigger than 1/2, the 5-component system functions more reliably than the 3 components. And I'm sorry, all this nonsense was going on over here. Okay, so let's just a question. I'm not checking my. Let's see if we got anybody more than 22 people. No, just barely. Chat's quiet. I like this problem, and I would put something like this on the test. Okay, so what's the next thing? The next thing is this binomial mean, and this is a little bit This is a little, unfortunately, it's also kind of ugly calculation, but I don't know any way of doing it. So any question on this problem? This was interesting. It relied on knowing the binomial distribution, the mass function. Okay. So okay, I'm going to erase this unless there's a question. Looks clear. Okay, so what do you think the binomial mean is? And before you answer, let's just think about a binomial setting. Suppose you have, so again, we're looking at binomial NP and applications of this random variable. Okay, suppose you have a multiple choice test. And I go through the lecture, and guess what the question I get after a minute? What kind of question we
Getting
get?
them all right?
So what does MC stand for?
Oh,
You know, MC, master of ceremony, whatever, and multiple choice. And suppose you have 100 questions and 4 choices. So naturally, this is a binomial setting because every question has 4 answers: A, B, C. And somebody always tells me at this point, and I'm teaching the lower division, they say, just choose B, just choose B. You've got these four choices all the way down, and so this is a binomial situation. What would P be in this case? What's your chance of getting this right? So what's your success probability if you just guess it?
1/4.
Yeah, so that's a quarter. And what is N in this case?
100 questions.
100. Okay, so if this scenario was repeated over and over again, on the average, use common sense. What do you think? What kind of score would you be getting if you just guessed every single time you took the test over and over? What should be your what's your mean? So in other words, I'm trying to see if you guys can if I can avoid the washout. Can.
The expected value of.
Yeah, what would E of X be?
My intuition would say 25%. So 25.
Yes, it is 25. But so if this was, in this case, again, I'm in the washout, but if it was N and P, what do you think it would be? What would fit the crime? You know, what's the evidence?
Should I say it?
Yeah, yes. We're in
Okay,
a rush.
NP.
Yes, very good. And remember, NP is not equal to P. No, that's a different class. No, NP, and it turns out you can also compute the variance. I don't know, anybody who had statistics?
Can we write that somewhere else because it's really, really hard to see?
Which one? The E?
The expected value.
Okay. I told the other class I'm done with this situation. I'm done with these primitive situations. I can't wait to get back to one-on-one teaching. I'm just tired of this. I'm just at some point you start to rebel, you know. And I used to have enough money to scare people off with lawsuits. I don't anymore. Okay, so EX in general is NP, and it turns out the variance for whatever it's worth is NP times 1 minus P. You might have seen something like that in the normal approximation of the binomial. But anyhow, so this is the thing I would like to get, and it's this NP, and believe me, it's going to extract something from us. But I'll do it I'm going to have to use notes so we can pop through this. So what do you think? Ross is a brilliant guy, and he wants to give you this, and he wants to give you this. So being brilliant, what do you think he's going to do? Is he going to do both of them separately, or what is he going to do?
If you just calculate the variance, you're going to need to get the expected value in the meantime. I don't know. That's my thought.
That's pretty good. What he's going to do something. Okay, this is what he's going to do, because I think it's brilliant. He says, okay, I will do this, and then he'll look for k equals 1 and k equals 2.
Okay. Well, yeah.
K equals 2. He can do the variance. So with variance as well, we know that's equal to what? Minus b squared, right? E of x quantity squared. So that will do it for him. Okay, so why am I doing this nonsense, this kind of proofy thing? I hate proofs in this class. Well, the techniques are used repeatedly through the book. And I got to show you at least something here, okay? Just something about this proof. I'm looking at this right here. So what is this, again? We expect NP will be the answer. It's intuitive, but we'll see. Let me check the chat. We picked up, oh no, we only picked up one person, it's good. Alrighty. And I'm afraid I have to use notes today. I don't like doing it. But again, X is what? The washout? No. So what is it that we have to calculate here? So his brilliance is to do this. He's going to just do this. Okay, so for people that are not, maybe CS majors in my class, they don't care about the proof, but how about the definition? What would be E of X to the K? We have to know the probability mass function in order to write this down. What is it? What's the definition of expectation? So this is an expectation of a function of X. So what you're doing here, I forget what proposition it was, 4.1 or something. You go ahead and do expectation like you normally would do it. But you put in the function of X here. So that would be I to the K. So that's the value of the function times the probability. What's the probability that the binomial, what's the mass function for I successes? What is it? I've got a chat. I thought that's what I wrote. Did I not? Oh, I meant it's N. That's how I write an N. That's my N. NP times 1 minus P. That's my N, sorry. This is how I write an N. Is that okay? Wayne? Did I just...
Fine. Yeah, I'm moving on to the next thing.
Okay.
Yeah, so we've got expected value is sum of xi times the probability of xi.
Right, which is what is this binomial probability? N choose I.
Right. Okay.
Times what? So what's the probability that it's I? So it's P to the I times 1 minus P to the N minus I. Okay, that's what it is. That's the definition of the expectation. We're using the theorem, so we're good with that.
Right. Yeah, and the I to the K, that's just the value of X that we're talking about. I think. Yeah. I'm just making sure I'm following. That's all.
Okay. Well, the function of the value was I, right? But the function of it was X to the K.
Yeah.
Good. So we got that. Now comes to something. Okay. It turns out that, look, if you have L equals 0, it's just 0. So it's legal to do this, to do some surgery here, and to put this as a 1. It's the same thing because it's 0, it's 0. Now I want to apply some amazing identity here. So this is the identity, which if you take combinatorics, you probably would have Conrad. This is N times N minus 1 times N minus 1. Why is that true? It's a little tricky, but I don't know what the best way to do this is. I guess if you expand out this side, what do you have? You have n factorial over what? You have an I factorial, so that'd be I minus 1 factorial. And this is n minus I factorial. Okay, so I'm expanding, this is this side, okay? Now this over here, so it would be, you would have n factorial on top, but what would you end up with? So it'd be n minus 1 minus I minus 1, but that's just n minus I factorial. over I minus 1 factorial. So we find out that the two things are the same. The only tricky thing is you have to go n minus 1 minus I minus 1 and figure out what that is. You have to keep track of the negative signs here. So this is n minus 1 minus I plus 1, which is the same as n minus I. That's the only tricky part of that. Okay, so I survived that, except I have a chat. Yeah, it was n the whole time. Okay. Now we have to use this. This is the crux to the argument. This is the crux to it. We have to use that identity in here. So what what has to happen? Well, I need an I to hit this and choose I. So I'm going to steal an I, steal Alpine. And now it went into that, so that means what's going to come out of this? Well, if you steal an I and you hit it with n choose I, you end up with an n. So I'm going to take this n over here. And the n, I'm going to steal a p there too. So you end up with p to the I minus 1. Let me get the more important thing here. I have n minus 1, choose I minus 1, and I have p to the I minus 1 times 1 minus p to the n minus I. This is part of the proof here. Okay, so it's beginning to look hopeful because there's an NP, right? It's beginning to look hopeful. And now we're going to move this back down to 0. And what do we have here? It'd be I plus 1 to the k minus 1, just rewriting this. And then they have this junk. You have this junk right here. Well, what is that stuff? Well, I guess I have to rewrite it. It's p to the I, 1 minus p to the n minus, or I minus 1. Actually, this was an I. It was I minus 1, but then when I started the I at 0, this becomes the I right here. Okay, so this is the critical step now. This is NP, and this
I'm
is.
sorry, in that step, you reordered the sum?
Yes, I started I equal 1, so now I'm starting at 0. So that means whatever I
Okay.
see in I, I've got to add 1.
Gonna index it up, okay.
Yeah, I've got to index it up, exactly, right, very good. So anyhow, what is this? This is some expectation here. It's expectation of y plus 1, so plus 1, so y would be the I to the k minus 1, where y is binomial n minus 1 p. So this is kind of like the restaurant problem and every other problem of that nature, where they're sort of reducing things to sort of recursive. Let me clear this off. Okay, so this is what I need here. So let's just let's see what would happen. Now this is going to be able to handle both cases, the variance and the expectation. I won't have time to do the variance because I want to get to the test. But if we take k equals 1, if you set in this formula that we developed, if you set k equals 1, then what happens? You're looking at e of x, because k equals 1 equals what? NP times, if k is 1, that's 0, so e of 1 is just 1. So this establishes this right here. If you set this, I don't have time for this, but if you set k equals 2, then I would be looking at e of x squared. It's going to be what? What would come out of this here? If x is 2, well, I've still got, why do I have to do x squared? Well, I have to do that because I'm looking for I'm looking for the variance. So let's see, how hard is this? It's probably not very bad if it's two, let's check this. I hope I don't mess up and very like, it's two, so I need the expectation of y plus one. So that would be what?
I'm struggling to see where y is. Like, are you
Right
trying
here.
to define? Oh, okay.
Oh.
Binomial. Okay, I see it now.
Yeah, yes. So of y plus one. So you're gonna have. You see, if it's just y, it's n minus one times p.
Mm-hmm.
But because it's the plus one, let me check to make sure that's right. Yeah, that's right. And it turns out that whatever that is, I mean, it's some expression, but if you want to get the variance, it's just going to be that expression, whatever that is, minus what? And it turns out that it all boils down to NP times 1 minus P. I don't have the space or the time or the inclination to finish off this ugly kind of algebra type stuff. But you see, what was his genius? He did two things at once. He got two for the price of one here. And if you're going to go on in statistics, I got at least 4 stat majors. What's going on here is he's doing something with something called the moment generating function. And this is a slick way to find all the moments. So the first moment is the expectation, the second moment is e of x squared, and the third moment, so forth like that. Okay, now I'm getting close to the test. The critical distribution that we haven't discussed is the geometric distribution. And this is very simple, you guys, but you just got to pay attention. So can I erase? I'm going to erase this stuff. I've got all the critical things in here, and I've eliminated some things that were important that were in the book. So this is, if you took notes, this is what you need to do this kind of calculation. Everything that's critical is in here. Okay, so what is the geometric distribution? How is it? What does it model? What do you use that for? So,
Geometric distribution is.
go ahead.
Isn't that the one where you keep doing something until you get a success?
Until you get the first success.
Okay.
It goes like try again until you make it, something like that. Right. So this is, so x counts what? X equals the iterations or reps. I like the word reps, maybe because I used to lift weights. Reps until the first success. So for those that are lost or something, what would be an example of this? You're flipping a coin, you're tossing a coin, right? You're tossing until you hit the first heads, right? So what would be the possible outcomes of that experiment? Just so you get an idea of the sample space. If you're tossing a coin, what would that look like? Well, you might get your first heads right off the bat, right? If that didn't happen, well, then maybe this happened, or maybe this happened. But there's something you got to notice about this that creeps up on us. That's an infinite sample space. I mean, it's countable, it's discrete, but that's infinite, right? You could have a very long line of tails before you hit your first head. But anyhow, having said that, what is the probability mass function of this thing? So what is the probability, in, say, this case, x equals I? What's happened here? Well, you have a long string of failures before you get that first success. So each failure is what? 1 minus p to the 1. And then your last success is what? That's the probability mass function for this. Now, I do not want to fail today to give you this tool you need, and I'm between a rock and a hard place because I need to compute what the expectation is of this random variable. So let's just see if our intuition is serving us. What if we say p is a half, okay? What do you think, on the average, how many tosses of this coin do you have to get before you hit your first success? Any clue?
My guess is 2.
Your guess would be right.
Okay.
Okay, go immediately to statistics. Okay, now I know your new major. Okay, so it turns out that the mean, so E of X equals 1 over the success probability. In this case, it was what? It's a fair coin, P is a half. It's 1 over 1/2, otherwise known as 2. And that's unfortunate because that was the last red marker I had, and it just died a natural death. Okay, I need to, of course, I need to prove, that that's the expectation. Oddly enough, this is truth, is stranger than fiction. It's the same thing you do with the restaurant problem and all that. You get some sort of recurrence as to what it has to be. And let me look at the time. 1:08. How much time am I supposed to have? 1:45. I think I'm on target to maybe be able to squeeze off the expectation of X. So let me go to my notes to speed it up. So let's start this off by a little simplification that Q equals, that's awful. Q equals 1 minus P. And we want to do what? I want to get this expectation of how is an expectation defined? So you can start at 1, but you will go to infinity here. So what are the different values it would be? So you could have I, and you could get the success on the ith trial, which means that I'm going to have what? So ith trial, it returns I, but what's the probability of this happening? Well, you had failures. How many failures did you have? Well, you had I minus 1 fails, and then you just hit your first success, okay? This is the expectation of the geometric random variable, okay? Again, why is it like this? Well, it's the value of the random variable times the probability. So what's the probability that you achieve your first success on the ith trial? Well, you had 1 minus P, which is Q. You had I minus 1 of those fails, right? And they're all independent. So the last one is a success, P. Okay, I'm not looking at the chat, so. Okay, so this is some tricky stuff here. So what do I need to do? So this is the trick. And I need to go I minus 1 plus 1. That's obviously the same thing, but the big question is, why did we do that, okay? Why do we do? Well, you're going to be able to, again, it's trying to get some type of recursive type action here. So this is, now you can distribute this. So one of them will have I minus 1, Q to the I minus 1 times P. And the other one will have Q to the I minus 1 times P. Now, this is the crucial thing here. If you add up all of the probability, all the values of the random variable, then that covers all the possibilities. You get 100%. So that this thing right here is 1. I'm going to do it in red, but my red markers have all died. But what about this? Okay, that's a 1, but what's this guy right here? If we're smart, we could start this one, we could start it back down at 0. And if you did that, it would be IQ error. Well, how did IQ error get involved? Okay, IQ P, Q to the I times P. But what is this here? This is it's kind of like what we started with. It looks like the same thing that we started with here. Okay, so that's just if you pull out a q, it's not exactly the same. See, it's q to the I minus 1, q to the I. So if you pull out a q, you end up with e of x, the thing I'm looking for. So if you look carefully at this, the thing I wanted now is expressed recursively in q times what I wanted plus 1. So can we do that math in our head? So let's put the e to the x on the other side. So what do you get? You can't write in this weird thing, but I know you can't see through my back. So e to the x times 1 minus q will be equal to 1. So this tells me that the mean is 1 over 1 minus q. But remember, q is what? 1 minus p. So 1 minus quantity 1 minus p is otherwise known as p. Okay, and that's the result. Okay, I hate to ask if there's any question, but even if you don't follow the steps, you should see that this is so similar to what we're doing with the restaurant problem, everything, all the good problems I've done in my class. We can get this recursive, we set it up as recursive. This is what's going on here. This is just done more mathematically than looking at a tree.
I followed the proof, just like I did it on my own paper, and I'm like, oh, good, I got it. But I guess my question is, we did reindex.
Right.
So what allows us to say that reindexing is like that also equals the expected value of x after you pull out q?
Because that's a definite. Okay, so that's q to the I minus 1. It looks like this.
Oh, I see it now, because the original one already was from 0 to infinity anyway. It's just
right. Right. You started at 1 because
we started at 1 because the 0 doesn't matter.
Right.
So okay.
Okay.
I got it.
Okay, now comes the big thing is coming, the extra credit. This is the big thing, okay? If you get this, you will remember it fondly for the rest of your natural life. So let's see, what was our situation on that? Okay. Okay, so this is my recommendation for you guys. Okay, I'm going to erase this. I need space. Give me more space. Nobody talks like that. But wasn't there a commercial on TV with somebody? Oh, whatever. Somebody said, "Don't bother me, I'm eating." That was such a classic. And that guy's last name is the pro NBA. He was an NBA player. His last name was Dye. Okay. Anyhow, so what was this story about this? You were throwing balls into bins, right? How many bins? How many bins?
I'm not sure what you're asking. Is this something from the test?
Yes, we're looking at the extra credit.
The extra credit is in number 11 or is in?
Yes.
Hold on. I'm looking.
I'm looking at 2B.
2B. Okay.
And what was I hope I'm doing the right problem. I hope it's like we got the right test posted up. So what was that problem though? What was it asking? The expected number.
How many balls need to be tossed before we can expect exactly 2 of the bins to have at least 2 balls each?
Yes.
But the extra credit was for okay, what it says here is 5 points for a successful simulation. So I was assuming the extra credit would be to be able to simulate this, not to solve the problem.
Usually, this is my experience. Most students, except for very rare students, most students will simply simulate it and get a decimal approximation. And that I give 5 points for it because I had to write the program. However, you don't need to do any computer stuff.
if you can solve this exactly, that's the glory. And there's no small amount of glory with this. Let me tell you, for you guys, if you get this, it will be forever. This is not trivial. So this is my suggestion. You don't have to do it this way. Is why don't you start it off with 4 tosses, okay? And then start from there. So what are the different things that could happen in 4 tosses? Well, are you clear on the concept though? You want to know on the average how many tosses until you get at least 2. Is it at least or exactly?
And I hope
Exactly
until you get
2.
at least.
Well, actually, it says exactly 2.
Hold on, maybe I gotta reread this then.
So it'll be,
until we expect exactly 2 of the bins to have at least 2 balls.
right. So as soon as you get 2 bins,
Right. That's how I
with these
understand
2
it.
balls, or you can even say it. You can even use the English until you get 2 bins with 2 balls. Once you get 2 bins with 2 balls, you're done. And it could be 2, 3, or 4. But as soon as you get 2 with 2, so one of them could be more. So what I'm recommending to you guys to do is to break it down from the beginning, the start. Just say these are the things that could occur with probability that you will calculate. These are the possibilities to get started with 4. You start with 4, just 4 balls. So what could happen with 4 balls?
A success. We could get 2 and 2.
And you're done. Of course, there's 3 ways I can, but you can calculate that you're done. This is the easiest case. This is the easiest case. What else could happen? Let me check my notes here. What else can happen? Well, you know what? This is a possibility.
Professor, I had a quick question.
Yes.
While I was going through this problem, I came across like a forum problem where they discussed something similar, but it wasn't the same thing. But they recommended that this problem was similar to the coupon collectors problem. Is that true, or is that like something else entirely?
I wouldn't be surprised because all these are sort of similar. I mean, to be intellectually honest, as a graduate student, if you're taking a combinatorics class, they won't approach any of this the way we're doing. They use generating functions.
Gotcha.
They'll just do that. So they won't even talk about the coupon collector problem. They just say, here's a list of the generating functions. Take the one that fits your problem.
Okay,
but I think there's some value in trying to do these in the classical way. But what I'm trying to say is the way to set this up is with a probability tree diagram, and what are the cases that you would hit? So I guess let me start there. I guess I have the time to. So what was that other case that I had? That you're done, right? But so how many tosses did that take? That case? 4, right? And then there's a question of what's the probability that it's probably not so high, right? That you end up. That's what you got to calculate, right? Each of these different cases has a different probability. Can you give me another case? Can you give me another case here?
With 4 as well?
Yes, with 4 put in, it looks different.
All in one bin?
Yeah.
Right? So you're in that situation. Since I'm at the bottom of the board, it must mean there's only 4 cases, right? So what would be
3 in
3
one
and
bin?
1 and one of the other?
Yeah, there's one more, right? So it's really, you just have to calculate the probabilities of falling into these cases, right? Now, the purpose of being here is to say that if you're in this case, then we can use the geometric probability because it's over when what? What is your success probability here? You're successful when what?
If we get in one of the 2, yeah.
Right. So, so in this case, we've already given 4, right? So you can think of this probably, you've already done this. So if you want, you can remind yourself where you're at. And what are the three possibilities that can come out of this on the very next one? What are the three possibilities? Well, let's take a look, okay? Let me draw that bigger, okay? Just let's draw it a little bit bigger. So we're coming into this in this situation. I hope you can understand it. So what are the three possibilities that could occur now? Or maybe it's two. Let me check maybe it's just really two. Yep. It's two. Because either you put another ball here and things are prolonged, or what? You get another one over there and then you're done, right? So if you go down this route, you end up with that. How much more time is this going to be taking? So you just did one, kind of got one toss to get that, but plus what? This is the critical thing. How long do you expect on average to keep on tossing before you hit one of these two guys over here? What's your success probability?
Thirds. It looks like a geometric distribution.
It is. So what do I have to add here?
1 plus we could just label that. It's the same thing. It's like the step before it.
Well, we can't. Wait a second, though.
Plus 1 over 2/3.
Ah, yes.
Sorry, should I not have said that?
Now that you have the weapon, it's been weaponized. And what probability do you go down this? I go down this path. Because it's really. It shouldn't say 1. It was how many? Well, whatever. You get the idea here. I've got to figure out. I took 4 to get here, right? So should be 5, right? So at this point you've done. So at this point, I've done 5 tosses, and to finish it out, it's going to take 3 halves more tosses on the average. So this is telling me what's happening here. But to go down that route, what's the probability you would go down this route from here? Remember, it could go to any one of these bins. So what's the probability? Okay. But in this case, you're done. So what is the answer in this case? We're done now. So what? So 1/3 of the time, it's going to take this much time. And then what? 2/3 of the time, it's going to be what? You're done, right? It's just 2/3 of the time, it's just one more. Now, I did this a little bit differently when I was calculating. So you have to know what's the probability you land in this initial case. You have to, but that you can.
Hold on. So just one more. So it would be a total of 5. So we should put 5 there, not 1?
Yes.
Okay.
Well, it's yes. Right. If you're counting from the beginning, from the beginning, it's 5. So this one ends at the 5th toss. This one over here, it's like you're punting. You're waiting, but you're waiting until you get a success here.
Mm-hmm.
Let me check my notes to make sure I'm not lying about the answer. Well, I don't. I did it a little bit differently, and I don't want to be mucking around with the algebra. But you get the general idea, right? So what you have to do, the work on your part, is what case are we in here anyhow? We're in this case A, right? You have to know with what probability do you end up in case A after 4 tosses? Because those would be your initial, right? You got to figure out, well, you're taking the expectation, but it's weighted by what the probability of these different cases. You understand that, right? So this is case B, C, and D. So that's sort of a combinatorial mucking around to get the. to see if they're on board. I mean, how likely would it be that you end up in one of these cases? You'd have to count, right? How many ways can you assign 4 different balls to distinct balls to 3 distinct bins, right? We know that that's multinomial coefficient, right? So you can do that sort of by formula. But in all these formulas, what's your denominator? Or maybe I'm getting ahead of you. What's the denominator? You have how many balls? You have 4. I'm getting these basic cases. You have 4 balls, and how many vectors can we make out of them? Each one has 3 bins, right? So what is that? 3 to the 4. Yeah, you're kind of indistinct there. I couldn't hear you.
Yes, 3 to the 4.
Yeah, 3 to the 4.
That's what I said.
Maybe you already did this. I don't know. You could have already done this whole problem.
I did it without the geometric distribution, and it took a long time. So, like that's one thing that I'm noticing with this test. It's like, man, I feel like there's probably other things that I could do to make this go faster, but I'm brute forcing a lot of things.
Well, the good thing is, if you take this shortcut, or and this was a shortcut looking at the first 4 balls, right? Starting from
Yes.
the
No, well, I mean, I did do that.
Oh,
I
okay.
did. Yes,
Power to you.
without a
Power
doubt.
to you. Well, then I'm not going to ask you because other people are listening, but you must have gotten probabilities for these cases.
I didn't do cases. I did it just to see, okay, well, if 4 balls were thrown, what would be the probability that our trial would be over? And just to say that, okay, well, since it's less than 50%, I have to keep going. I have to do it for 5. And then, yeah. And so I did, and I did it for 5, and I found the probability for 5.
Okay, I could be wrong, but I think the use of probability tree diagrams is the best way to do this kind of thing. I think.
In a way, I mean, I did make a tree diagram. I did, and it filled up a whole page.
Well, let's do this. What should be, in my opinion, what should be the probability tree diagram? You start, right, and you have how many cases? Really, this is case A, right? So to get started with this, and whatever happens after it happened, one of these is done, right? So this one is done. But don't you need to calculate these individual probabilities that you land in, like, and what's the probability that you land in case B? We could calculate that, right?
Right. I mean, I did. I know what the probability is. I have it right there in front of me.
Well, then it goes down from here. This one doesn't go any farther. So this
Right.
is what? So this is 4. This is whatever probability this is times 4, because you took 4 tosses to get here. So whatever that probability is times 4, and then so forth for these other. I broke these other ones down as you saw, right, into 2 or 3 cases each. Okay, so you did get a number. Why don't you email that to me? Well,
I'm happy to. Or when is your next office hours? We'll see if I can make it.
I don't want to make you come in. It's late at night. It's at 6:30 to 8.
6:30 on tomorrow or
today.
Or what?
Today.
Oh, today.
6:30 to 8. But I mean, you could just email. This is a very computational problem once you figure out what you're going to do, and it's easy to make a mistake. But I'd be curious if you got the same answer I got, and I'd also be curious if the people who are simulating it, if their answer coincided with yours. Can I ask the general class at large? Did anybody write a simulation program? I'm looking at the chat. I don't see. Did anybody start the test yet? No. Okay, it's quiet. It's eerily quiet, like the calm before the storm. But my experience teaching this course last semester is at least 3 guys, and there are 3 different groups, did a simulation to get the answer. I mean, it doesn't rule out the possibility there's a really simple way to do this. Did anybody consider doing the complement? But I don't know that would get the expected value. See, expectations are easier to do. There might be a really quick way to do this problem. I don't know. Okay. This is the only way I could think of. Okay, hold on a second. Okay, so I owe it to you guys to talk about the incident insanity, unless there's any more question on this. True, you know, this is only 10 points of extra credit, but the value is not in the. Oh, go ahead.
Is the instant insanity is an extra credit problem?
No, but some people have, they asked me how, you know, they weren't. Basically, they turned in the test early and they didn't do it, and I'm wondering. I didn't think it was that imposing of a problem, but maybe I should just look at one case of it. Give me the hardest case of it that you saw. I mean, I'll do that. Unless somebody has a question on this.
It's that okay, I looked up. I can actually. I don't know if I should link it to everyone.
Just
But
say
you did suggest to look up ways to solve.
yes.
Right. So and I did, and I found a page. I found a page of someone who had some really good ideas for like, okay, well, just to solve these in general, make a graph. So and I'm like, okay, great, I'll do that. And I saw how the graph was used to like show that something like basically translate from the graph to a solution.
Yes.
Awesome. So all I have to do is try to make, basically make 25 graphs and check each one and see if they're solvable.
That's where
That took
having a
all
group,
day.
that's where having a group comes in. You delegate it. Like
Okay.
somebody, if you got 8 people, how many graphs does each person have to do? it's an arithmetic problem. See, 25 divided by 8, it's essentially 3, which doesn't sound so bad, right? But if you have one person that knows what they're doing and 7 people that have no clue, then,
Right.
then it's not going to go that well.
So,
you can't do the division. I was
right.
thinking I could do one of them. I could try to do one. What was the hardest example? I'll just hit the hardest one.
I mean, okay, well, the one that I feel like should have a solution but doesn't. Let me go back to that one. Hold on. Let me get my notes.
Yeah, I'm gonna get my notes.
The where the E block has a yellow, or excuse me, has a red,
Yes.
and the B block has a green. I feel like that should have a solution, but I just can't find one.
Okay. This is real time now because I didn't. So I'm putting myself on the line here.
Okay. Well, the point is, I don't think it does have a solution.
Right.
So
I'm willing to
I just
look.
want to be able to like look at it and go, okay, no, it does not.
Yeah. Well,
Okay,
it might be a little more complicated. Okay, so we have 5 cubes, right?
Right.
Traditional instant insanity has 4, but we have 5 cubes of 5 colors. So I need some help. I can't use my glasses.
So really
Do
quickly,
you need some
Anne,
help with drawing the graph?
I don't have time really to draw the graph. I'm going to see if I can cheat it somehow. So
Okay.
what are my choices on A? So what are the choices? We could choose opposite pairs. Purple and yellow is one possibility, and red and purple. That's it. I can't use those purples because I'll have a surf feed of purples. And they won't be able to hide them all. There'll be no solution. But did I do it again? Oh my gosh, it's so frustrating, guys. And some of you guys have become professors yourself, teachers, and it's just okay. So A was one. What are the choices? Purple, yellow, and what? Red, purple. Yes or no? You're good with that, right? Those other the purple pair. Forget about it. You can't use it. Is that clear? I mean, it should be clear, right? If you look at it.
This is a table. This isn't a graph.
Right, but I'm looking at the original data, okay? And I see that there's a lot of purples, and I cannot use those two purples there because there'll be no way to get a solution. Most four of them can show, right? So you're going to get. How do I know this? Well, how many purples show on? If the thing is, if I choose that for purple, I'm going to get 3 purples showing on A, and I'm going to get 2 purples showing on E. So that's 5. So there's no solution. I hope you guys are good with that. What about B?
Help me with B. So this is the critical thing. So black. What did you say, Aim? If this was green? Green?
Yeah, the one that I don't think has a solution was
Green.
the B block has green.
Red, green. And what's the other one? I'm missing one. Black, green.
Yellow,
red,
green.
Green and yellow, green. Green, yellow. Okay, C. Hopefully I can speed up. I don't know why I can't speed up. So green, black, green. Black, green. There's no black, green on this. C.
It's green, green,
Green, yes.
green, blue, red, blue.
Green, or black. I can just do them in alphabetical order. So black, green, and
And black, red.
black, red. Okay, I'm almost done. Sorry it's so slow. Now I have yellow, green, green, yellow, right? Green, yellow, black, red, and red, yellow. Yes. One more. See if I can survive the day. And I think you said you wanted to put what down here?
I wanted to check for red, and I don't think
red,
there's a
red.
solution, but I want to see.
So purple, red is what you were going to go with, and black, purple.
Okay, this is my comeuppance. So quit myself. I don't have my red. That's probably it's going to kill. I don't have my red marker. Okay, that's going to cause trouble. Okay. What makes us think? Okay, so we have to show. I think what you're trying to show is and this isn't a washout. So show no solution, right?
Yeah.
How to show that? How much time do I have?
I'll go until you have it.
I've got 6 minutes. Because that's not
Yeah.
fair, you know? I don't care how smart somebody is, and I'm not that smart. But I have had some experience in these puzzles. I think that's unfair to do it in 6 minutes. But let's see. Does anything jump out?
So, I mean, the thing for me is I literally drew a graph, points, lines, those kinds of things. I'm not sure what method you're using.
That's the genius of Mr. Tute,
Okay.
or Tute, his 16-year-old's mind, you know? You
Okay.
know, genius. But we're not, because I have this restriction here, that's why I'm looking at if I can just see it, you know?
Huh.
So let's see what the story is with greens. If you took green, then you would be forced to, I'm just saying if, I'd like to eliminate some possibilities here. If I took this one, right, then for one of the threads, right, solution threads, I would have to go this, right? And what would have to happen down here? Green and red, green and black are fulfilled, so therefore this has to be this, right? I'm going to need 2 purples, but I can't take this one, right? So I'd have to take this. I have to take these 2 purples. But you see, if I take this purple, I'm already done with red. So there's a red here and a red here, so that's too many reds. You get that? I can't take this. So what's the upshot of this? Did I go too quick, or are you guys good with that?
More just I'm not familiar with how to solve it with this in this method.
Because I'm solving two opposite sides of the tower. That's one
Okay.
thread solves choices for the front and back, and the other one will do the sides.
Okay.
The-
Yeah, right.
they're
Yeah, okay.
autonomous. This was to
Yeah,
change.
that's it. So we have to use.
You can't.
So you're
use-
saying that we have to use the black and the green for this one?
No. I'm saying if I use the green.
Okay, if we did that.
Right, I'm going to try to eliminate that possibility, you see, because that would make a smaller puzzle for us to solve. If I
Right.
took the green, I would get in trouble because I can't extend that thread. You see, if I take purple, red, I've already done with red, and so I can't do this one. But let's see, hold on a second. Maybe I could take purple, yellow here. Yeah, but okay. So if I take this, reds are done. Oh, maybe. Okay. Oh, hold on. This is what I get for. Okay, so we took green. You had to take black.
Okay, I have one solution from using my graph method. So if we did black, green, that would be with the B block, that would be with the C block. You could go from yellow to red with D.
Okay, hold on. But I mean, okay. But I'm trying to eliminate the green pair. That's what I'm trying to do. So if you take purple, red,
Okay.
I guess you could. Okay.
You could go from red to yellow with the D, and
You
then
do
from
this?
yellow to purple with the A. Great, awesome.
Yeah, so,
That's
okay,
one cycle.
It looks like you can do that. So this is assuming you, and I don't think I had any other choices. I think this was it. So we were forced into this. So that means that the other one, the circles, has to take red, purple. And in order to get that, the problem now is you just know there's no way to match. I don't see another. Oh, I see this black, purple down here. So it has to take this. Okay. It has to take that. So what purple is done, but I don't have other purples. Okay. Well, we have to just see, can this be extended here? You've got red, purple, black, purple. What do we need to do here? If you take black, red, you're done with reds.
Can you do black, green on C, and then D, green, yellow, and B, green, yellow as well?
But
Our problem, okay.
You know something. If you took, what do we have so far? You got a black, purple, and you got a red, purple. I'd like to show that I can't continue this. But if you guys look at how many people do we still have in the game here? We got 22 people. If you look at this, maybe. Okay, go ahead. Who spoke ahead there? Maybe you might be right.
I'm looking at it from a different perspective. I'm looking at it from a graph. But once you get to red, you end up having to go to black again. We've already hit that. Oh wait, hold on. No. A, E, C.
I don't know. I can't.
And then.
But what about? Wait a second. Hold on a second here.
C,
I think I
black,
heard a solution.
green, right?
Black, red. You mean? No, black, red. Hey, hold on a second here. Hold on a second.
Yeah.
Yeah.
There we go. Okay, awesome.
This looks like there is a solution.
Fantastic. Okay.
But I don't know. I don't want to say in case I made a mistake. So,
Okay. Well, I'm
let's
gonna write down
clarify.
the cycle for it.
I
The
think
way that I'm
that's
keeping
correct.
track is just if I can write down a cycle, I'm good to go. Alrighty. So it was okay. I'm good now. I found a solution to that.
Oh well, then that means that's one of
It is a
those has a
possibility.
solution.
Right. Yeah. I sat with this one for a while, and I eventually just gave up and said,
But
okay, I can't
See the
find it, so
technique.
it's not
We
there.
knew we could eliminate two possibilities, and that made it a lot easier to you know what I mean, to figure out what had to be, how it had to be.
That's fine because we went purple, yellow, red, along back to purple.
So,
along
Professor,
A, D, E.
would you? say that this method is preferable to the graph method where you have to find two Hamiltonian cycles?
It's not, but there's a special situation here.
Okay.
We know that this opposite pair, I forget it's purple or whatever it is, that's out of the picture, and this one's out of the picture.
Oh yeah, but you can represent that in the graph as well just by removing those two, because that's what I've done.
It really jumps out this way. I feel
because those are just loops off the graph node.
I know, but to me, if I can get it reduced like this, and when it's only 5 or 6 cubes, I'd rather do it this way.
Got you.
But you might ask, what if one of these doesn't have it? I mean, I don't want to. I don't want to cheat the problem for everybody else. I want everybody to experience it. You know what I mean? But there is a potential that every choice works. You know, and there's a potential, a probability 1 that this is solvable. But I don't want to. Well, certainly you can't put purples in there, right? You can't make it worse with a purple.
So you mean solving it without using the question mark cubes, right? Or tiles.
If you don't use I'm trying to remember. If you don't use the face, those are faces of cubes.
Yeah.
I'm not sure that you might get hit with too many purples.
Yeah, I don't think that there is a way to solve it without using the two faces that you've selected as random because of that double purple. Right,
because as soon as you get more than 4 purples showing out, that's not going to be a solution.
At least there's only 25.
Well, it depends on the size of your group. If you're one of those, who am I talking to? So it was a pleasure. Chris. So it depends on how many people in your group. If you're working by yourself, this is bad news because you know what I mean. It's like 25 cases to check. But if you're in a group, you could divide it up, and you know the purples are out, right? And so,
yeah. I mean, I might be doing it the wrong way, but I'm almost done writing something that will, because it's only 5 cubes, I can just brute force it, and then I can just do the proof on a graph for each solution that the computer finds.
Oh, are you using a program for this? I guess you are.
I'm writing one, yeah. Well, I'm almost done with it. I'm debugging it right now in class. I'm very thankful for the extra.
I know that you didn't do it, but I think somebody emailed me and said they went to the GitHub, you know, they said the program wasn't working right. They failed to notice that there's a little disclaimer. It said, please submit $25 if you want this program to work right. We'll tell you what the error is. It's execution error. It's not syntax. People think they can get that stuff for free, and this is this technique of requesting money to fix the linchpin is that's as old as civilization. Okay, any other case? Any other case, you guys? Or are we done? Are we out of time? Oh my gosh, we're out of time. Oh my gosh, I'll stick here. I'll stay here. You guys have your test. I'll help. But I'll help if anybody wants to.
Hi, I had a question about the instant insanity. I found a solution with loops.
You mean using the tut graph?
No, I made the little cubes and I found but every one of them has a loop in it because I did it with the random ones, kind of thinking that oh well, it's a free for all, so if it happens to be this one, then the solution works. Mm-hmm. So does that mean that I guess there are 2 solutions to this because you found one just now?
Oh, solutions are not unique in general.
Yeah, just one solution.
No, they're not. They're not unique. So you could have multiple solutions.
Okay.
In fact, that's the mystery. I've been assigning this stuff for a long time to the CS class I teach, and it turns out that when you have huge puzzles, like say 80 cubes, 80 colors, they may have multiple solutions, but not that many of them. It's something that we don't understand why that phenomenon happens, but definitely you typically get no solution or some, but you don't get an explosion of solutions if it's for randomly, well, you just don't get it. If it has a solution, it doesn't mean it's got tons of solutions. It has some, and this goes all the way up to puzzles of size 80.
Okay, because I didn't understand how to do this because when I looked at the graph theory for it, everyone online does it with 4 cubes.
Oh, right. Oh, okay. Let me, do you want me to make the graph? Or do you have a moment? I mean, do you have time or do you have a class?
That'd be great.
Do you have class or?
I don't have class after this.
Oh, good. Okay. Let's just make the graph for the whole thing. Okay.
Okay.
I think AIM has a class. Are you gone, AIM?
I have to leave, yeah, in a few minutes, but go ahead.
Okay. Was there another question you had quickly so I can?
It was mostly on this question, so just the fact that it was just taking so long, that's all.
Yeah. Okay. Somebody's got a chat, which I totally missed here. What did they say? Okay. Thank you, Edwin. Thank you. Okay. Let's okay. So, what did you use? Let's see. So let's make the graph now. We've got 5 cubes, so you go by color. So what are our colors? And what's my spatial? So my colors are what? Black, red, yellow or purple. Green and yellow, right?
Yes.
And yellow. Okay, so let's start putting them in. So I'm not going to do the deselected purples, okay? Because we know they can't be used. So we could go yellow, purple on A.
Wait, why can't the purples be used?
The purple pair on A, because if you use that, you'll have too many purples showing. Because if you use the purple, if you're going to use the purple, that means you're going to get 3 let's see, at least 3 purples out of A, right?
I found one with purple with A.
I don't see how that can happen because okay, let's take a look. This is an issue. Let's take a look at what the problem is. So I have on A, I've got purple, red, purple, right? And this is yellow and purple. So no matter how I orient this cube, okay, so you're saying okay, so we have these 2 showing, right? So then what about the other opposite pairs?
I got one if the red is showing, the purple is showing, the purple.
Got it. Good. So how many purples do you have here?
Or no, I configured the cube so that the red, instead of another purple, a yellow is showing.
I'm not sure how you can do that because this is the cutout, right? So this is a cutout. You can't change the puzzle on A. So these are opposite pairs. These 2.
Yeah.
These 2 are opposite pairs, and these 2 guys are opposite pairs. So if you show purple, you're going to be showing purple yellow or purple red.
Not if you flip the cube.
Well, the opposite, okay, the opposite sides of the cube doesn't change if you flip it. They're still the opposite pairs, right?
Right.
Let's look at a cube right here. Can you see this one?
Yeah.
Okay, so the opposite pair, these are like 2 opposite pairs. My fingers are on. No matter how I flip the cube, they remain opposite pairs. So what gets shown on the outside are like if those 2 are hidden, then I have 2 opposite pairs showing here.
Here, let me. Hello.
Yeah, hi.
So I made my cube, and if we do purple, red, or if we turn it this way, so I get a purple, yellow.
Okay, let's do it, Catherine. Let's just tell me what your opposite pairs are on your cube. Just looking at it. What do you have? Just the opposite pairs.
The opposite pairs, so yellow and purple,
Yeah, purple, got it.
purple and red.
Purple and red. What else?
Purple and red, yellow and purple, purple and purple.
Okay, this is my point. Okay, everything's in front of you right now.
Right.
No matter which two pairs you choose to show out, okay, you know, the back and the front and back and the sides, like no matter which two you choose, I see you chose these two, right?
Yes.
So you choose red and okay, so red and purple to show out, and purple and yellow.
Yes.
Wait, but you didn't choose purple. So you choose these. So you have two purples. Okay, I think before. So for some reason, I thought you told me that you had chose purple here.
No, purple and yellow.
Oh, okay. So so you've got two there. So okay, so that was one cube.
Yes.
So, my point was that you couldn't choose purple. You have too many purples. So maybe we just got miscommunication.
Yeah. Okay.
What was your other? So what are you going to choose for your other cube? So that's cube. So B and E, you're not going to use purple there, or
Yeah, I didn't use purple on B. But I did use purple on E.
okay, let's check E then. Maybe that's the problem. So I'm going to have to go backwards. Let's check E. So what are the opposite pairs on E? Maybe you could just tell them to me.
My opposite pairs on E were, I got a purple, black, and the question mark.